Hi everyone, this is Giri, Application Engineer for Mirabolous Design, and today we are going to go through ARM-based modeling using VisualSim Architect. So VisualSim Architect lets you do system-level modeling and power performance trade-off analysis through a graphical user interface-based tool. VisualSim Architect ships with a large system-level modeling IP library with fully configurable components. It runs on a discrete event simulator and uses statistical extraction tools to analyze the system behavior and optimize your configurations. It also contains libraries for requirement tracking and regression. VisualSim Architect enables system-level exploration through a repetitive process. It starts with an architecture block diagram, which is translated into a model using the system-level IP present in VisualSim Architect, and testing this architecture using workloads. Each component present in the architecture can be parameterized and constraints can be applied to them. After finalizing your model architecture, you'll be able to do a regression sweep and generate statistics and specifications for all of the subcomponents. And this trade-off can be repeated to optimize your architecture. VisualSim contains a lot of ARM-based components, specifically processor cores. We have the Cortex M series, A series, and Neoverse processors, and also a customizable processor implementation, which lets you customize the instruction set, the pipeline stages, the execution units, and the instruction execution delays. VisualSim also has the ARM bus architectures like the AHB, APB, AXI, and ACE. VisualSim also contains Corelink CMN Mesh Network libraries, which lets you model the CMN 600, 700, and Cyprus Mesh Networks with all the requester home nodes and a setup library which lets you define the system address map, quality of service, and a routing table. Additional hardware components for the ARM DSU or the dynamic shared unit, system level caches, coherent caches, DMAs, memory controllers, DRAM devices, interfaces like the PCIe 6, the CXL3, and Ethernet interfaces, along with the peripherals are also present in VisualSim, which lets you build a complete ARM-based SoC. So to show you an example of how easy it is to build a model up using VisualSim, we go into the library over here. You can drag and drop your processor cores, your memory devices, the memory controller, and a DRAM device. You also have bus implementations over here. And for the CMN mesh network, you can drag in your router devices, and connect them up as simply as that. So now let us look at a few example models that we have and take you through the kind of trade-off analysis that can be performed using VisualSim. So the first example is multi-die architecture with Neoverse N2 core clusters. The first part is getting a block diagram ready of the architecture in mind. So this example has a 2-die architecture with 2 Neoverse N2 core clusters present on each die. A CMN mesh network, specifically the CMN 600, is used for routing the requests. Data requests are routed to one of the 2 SLCs present on the multi-die architecture, and the routing is carried out based on the definition present in the system address map. There is an on-die DDR memory for data storage, and UCIe interconnects present between the dies. This block diagram is translated into VisualSim, and this is a snapshot of the model. All the components present in this model are fully configurable through a set of parameters. The clock speeds, the buffer sizes, the data width, and flit sizes can be assigned per device. Here it would be for the DDR memories, memory controller, the router devices for the CMN mesh, the CMN interface blocks like the RNF, the HNF, and the SPSX, the Neoverse N2 cores, and the cache devices present in the architecture. Now let us look at how the Neoverse N2 core clusters are built. So the N2 core cluster has a shared DSC connected to the cores through a CPU bridge. The number of cores in the core cluster can be configured through the parameters, and they are dynamically instantiated at the start of the simulation run. In this example, we have 4 cores per cluster. Each core has an L0 cache, the form of an MOP cache, L1 instruction and data caches, and a shared L2 cache present in the private caches. Each core can be run in lock or split mode. Lock mode is used for redundant execution, specifically for high reliability systems like the automotive systems, and it can be run in split mode when cores are operating independently, which is ideal in the case of general purpose computing. The VisualSim behavioral flow is used to control the instruction execution on the processor cores. The behavioral flow can be changed to run instruction sequences in any configuration. For example, we can choose to run a trace file, which is extracted from either a Gen5 fast or a cycle model, converted to CSV format and fed into VisualSim, in order on each core present in a core cluster or parallelly, based on the way the behavioral flow is constructed. The statistics that are calculated and can be viewed at the end of each simulation are the power consumption per die, workload completion latencies, buffer occupancies, UCIe, bandwidth, delays, the number of requests that go to your memory, cache statistics like hit and miss ratios, the total number of requests, overflows, and so on. An example experiment run on this architecture is running the router and memory device at a specific clock speed, and then checking an alternate configuration where the clock speeds for these devices are reduced by 50%. We can see that this leads to a 0.63% increase in the latency per cluster for completion of the software execution, and a 0.013% reduction in average power consumption per die. This is the kind of trade-off analysis that can be done to optimize your overall architecture. Now let us look at a second example with a CMN Cyprus 4x4 mesh. So in this mesh, we have multiple requester and home nodes, 19 requester nodes to be exact. And we also have interfaces to PCIe, CXL, and ACE through the HNP, CCG, and HNI nodes. So this block diagram from the ARM Socrates builder is translated into VisualSim, and this is a snapshot of the model. So the requested devices in this example are connected to traffic-based cores, which can be replaced by processor cores to simulate execution of trace files or workloads. PCIe 6, CXL3, and AMBER ACE buses are used to interface the I/O devices with the HNPs, CCGs, and HNIs. System address maps are implemented at each requested device. And in the case that the system address mapping is not present for a specific request address, a global system address map is defined in the CoreLink setup library. The routing strategy in this network can be a choice between static routing and XY routing. In the case of static routing, the user will be able to define a routing table, which will be looked up when any request enters the mesh network. The clock speeds, flit sizes, and buffer sizes are configurable for all the devices present in the mesh network. The memory sizes, clock speed, and device type are configurable for the DDR devices present. You can see a snapshot of the PCIe 6, the CXL3, and AMBER ACE bus interfaces present in this system. The following statistics can be viewed at the end of simulation for this example model. We can look at the average and per access throughput for each RN device, latencies for the RN devices, throughput at the system level cache slice or the HNS, the buffer occupancies at the routers, cache statistics, and also the memory statistics for the DDR5. An example experiment run on this architecture is testing the average throughput at the RN devices with 3 different traffic rates, with the traffic-based cores generating requests every 1 microsecond, half a microsecond, and quarter microsecond. We can see based on the final results that the average throughput increases proportionally to the incoming network traffic, meaning that the architecture designed is robust. Now let us take a look at how we can run regression on a model present in VisualSim. Through the VisualSim PostProcessor tab, ranges can be assigned to a set of parameters to run a batch simulation. And on selecting a specific configuration and the plots that are required at the end of the simulation, we will get 2 script files that are generated, which lets you run the batch simulation either on a single thread or multiple threads. So multi-core simulation is supported through VisualSim. So let us look at an example where the device flit sizes in the CMN 4x4 mesh are varied between 16 and 64 bytes with a step of 16 bytes. The output plots from all the configurations can be combined and then compared. We can see here, we can assess the mean network and end-to-end latency for all 4 flit size configurations by combining the plots from the simulation runs. The optimal configuration can then be chosen based on this comparison, and then the model can be altered. So concluding, VisualSim Architect provides a robust platform for modeling, configuring, and analyzing ARM-based architectures. It comes with a comprehensive IP library and easy GUI-based design, which allows design engineers to conduct early-stage trade-off analysis. We can achieve an optimized power performance balance through data-driven decision-making. For more tutorials and other architectural examples, you can visit our channel VisualSim Solutions on YouTube. And for assessing a trial version of VisualSim Architect, you can log into this link over here at our website, mirabulousdesign.com. So this has been me, Keshut Giri, application engineer from Mirabolous Design, presenting ARM-based modeling in VisualSim Architect. Thank you.